Delaware Tech, Chemistry 100, Chemistry 110, Gas Law Problems and Calculations. Shown here is a table of the 4 gas laws and 2 additional laws that we've already talked about. The combined gas law, which combines Boyle's, Charles's, and Gay-Lussac's, also known as Amundsen's law, into one formula, P1 V1 over T1 equals P2 V2 over T2. And then the last equation in this table is the ideal gas law, combining all 4 equations as a 2-step problem, a 2-condition problem, where we have P1 V1 over N1 T1 equals P2 V2 over N2 T2. And either one of these ratios of PV over NT equals R, the universal gas constant. We can also write this as a 1-condition formula where we just say PV over NT equals R and leave out the 1s and the 2s. So we have a one-condition version of this equation, and I'll circle that. And you can use this or this for 1. And then we have a 2-condition version, and we'll just forget about the R for now. And the reason this is so valuable is if you have only 1 condition for the gas, in other words, you're not changing anything, you just need to know all the different parameters, pressure, volume, number, and temperature, and if you know 3 of those, you can calculate the 4th one knowing the value of R. Or if you have a 2-condition problem where you know a number of the different parameters and you're trying to find out one new parameter, or maybe the one older parameter that you're missing. Say you know P1 and V1, but you know P2, but you don't know V2. You could use this to calculate that if you know something about all of the parameters except one of them. So we have all these equations. In addition, we also have Dalton's law of partial pressures, which is not shown here. That one just says that the total pressure of any system equals all the individual partial pressures contributed by each individual type of gas in that container. So let's look at some typical problems and decide which formula, which law is the appropriate approach to solving that problem. So let's look at number 1. What is the total pressure in a balloon filled with 170 millimeters of mercury of oxygen and 620 millimeters of mercury of nitrogen? And you'll notice the only parameter we're talking about here is pressure, and you're given 2 partial pressures. So this tells you right away it's going to be Dalton's law of partial pressures. You merely add the 2 individual pressures if those are the only 2 gases in the container. In this case, the container's a balloon. You add them together and you'll get your total. So you would add 170 millimeters of mercury plus 620 millimeters of mercury, and you would get 790 millimeters of mercury of pressure for the total mix of oxygen and nitrogen. Now, I'm not going to go through the solutions for each of these problems. We've already done examples of these problems. This is just to get you acquainted with looking at a problem and deciding which approach is best. Number 2, I have 5.6 liters of gas, okay, that's a volume, at 1.5 atmospheres, or that's a pressure, in a sealed piston. What does sealed piston tell you? Well, sealed tells you that the number of gas particles, either as total particles or moles of particles, is constant. Nothing's going in, nothing's coming out. And then the question says, if I increase the pressure, all right, so now you know it's a 2-condition problem because you're changing something. If I increase the pressure to 3.4 atmospheres, what is my new volume? Well, in any of these problems, except for the Dalton's law of partial pressures, you can always start off with the 2-step or 2-condition ideal gas law, which is P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now we know either one of these equals R. We don't write the R in here. Why not? Because we might be canceling things in this equation, which will make it no longer be equal to R. So we leave the R out when we write a two-condition formula here. and you are told that it is sealed, so now I know that N1, the initial number of molecules in moles, is equal to N2, so I can just cancel the two N's. And it doesn't say anything about temperature, but let's assume the temperature is constant. There's nothing mentioned about it, so we're going to cancel out the temperatures, and we're literally just left with Boyle's law at this point. And you'll notice you're given three of the four parameters here. You're given the initial volume, the initial pressure, the final volume, the final pressure, and you're asked for the final volume. Now, what I recommend is anytime you have these kinds of problems, you immediately start with a table. And if it's a two-condition problem, you're going to make a table that has 3 columns. You're going to have your parameters in the first column, P, V, N, and T. And you're going to have your initial conditions, we'll call those number 1, and your final conditions, we'll call that number 2. And then you start filling them in. Well, you know that N1 equals N2. Sorry about that. And we're going to assume that T1 equals T2. A better written problem would actually state that in the problem. So sorry about that. Okay. And then we fill in the values for our initial P, our initial V, our final P, and then we solve for it. So I always recommend you build a table like this. Sometimes your table will only have one column for a one-state problem, and it'll have another extra column at the end for a two-state problem. So this will result in using Boyle's law because you're just dealing with volume and pressure. Those are the only things changing, and you've canceled out the other items. Number 3, a balloon has a certain pressure, a certain volume, and a certain temperature, and you'll notice the temperature is in centigrade. And if P remains constant, okay, that means you don't even have to worry about P. T drops to minus 20 degrees centigrade. What is my new volume? All right. So you have a two-step problem, and you start with exactly the same formula I wrote before, and I'm going to write it up here so it's out of our way. T1 equals P2 V2 over N2 T2. We can make our column of parameters. We'll have our first set, our second set, our P, our V, our N, and a T. And then we look at the question itself. We're looking at number 3, and we notice we have an initial pressure volume. And we'll write the actual volume here. I'm just going to put a check mark for now. We'll write the initial volume in here. We have that. We'll write the initial temperature, but you have to convert the temperature to Kelvin. You might want to do that right away, or you might want to do that in your formula. It's up to you. I recommend that you actually convert it right in your table. Leave a little extra space, add 273.15 to the 25, and you would actually write in here 298.15 degrees Kelvin in your initial temperature. And you'll do the same thing with the other information for the second condition. You're told that the pressure is constant, so that means this equals this. So you have that value, and you know that the volume is our unknown. And we have a new temperature, minus 20 degrees, and you can write the minus 20 degrees. Make sure you label that it's centigrade and that it's not the thing you want. Sorry about that. Not the thing you want. Sorry. Let's get rid of this. And we'll convert that one as well. So minus 20 degrees would be 253.15 degrees Kelvin. And we put that in our table. And then we have information that it's a balloon. So the balloon is sealed. So we're going to say that the N1 equals the N2 as well. So you'll notice if we know that the pressure is constant, well, then we can get rid of pressure because P1 will equal P2. And we know the number is constant because it's in a balloon, it's sealed. The only thing we're dealing with is the volume and temperature changes, and making sure that we convert our temperatures to Kelvin. And I'm going to, and that will just leave us with V over T in the first set equals V over T in the second set. And that's simply Charles's law. Looking at question 4, how many moles of gas does it take to occupy 120 liters at a pressure of 2.3 atmospheres and a temperature of 340 degrees Kelvin? All right, well, what you can see right away is nothing's changing. You're given one set of conditions, a volume, a pressure, and a temperature. So you can make your table to make sure you keep track. There's only one set of conditions, a P, a V, an N, and a T. And the only thing we don't know is N, so that's our unknown. Our volume, we have that. Our pressure, we have that. And our temperature, it's already in Kelvin, we have that. And this is a one-state problem where we're given 3 of the 4 parameters. And we know that P, V over NT, and we don't need to write ones here because it's only one state, equals our gas constant, R. And we know the value for R, or it will be given to us, or we can look it up. And the only thing that we're missing here is the N value. So I highly recommend that at this point, anytime you have a ratio or a fraction, cross-multiply to get rid of the fraction. So you're going to rewrite this as you're going to cross-multiply these two, and that will equal this, and R is just over 1, so we're not going to worry about it. So we end up with an equation PV equals NTR, or NRT is the way most people write it. And we're solving for N, so now we just divide both sides by TR. That'll cancel those two. And we end up with TR over here. And now our final equation is just a rearranged version of our ideal gas law. And I'm going to erase the clutter here, but we can start with the PV over NRT as our base form of the one condition ideal gas law, and we're just solving for N. And that's a pretty straightforward algebraic equation to manipulate. Let's look at question 5. A sealed commercial, sealed, all right, you know right away that the N is not changing. Sealed commercial airliner has a pressure of 1.00 atmospheres and a temperature of 25 degrees C. Anytime you see degrees C, you know you have to convert to Kelvin. At takeoff, if the temperature of the airliner drops to 17 degrees C during the flight, what is the new pressure? Well, it's a two-step problem, or a two-condition problem. You start with the two-condition ideal gas law, just like we. Oops, let me move that to a higher position. I'll move it up here. P1 V1 over N1 T1 equals P2 V2 over N2 T2. We make our table. It's got two conditions, 1 and 2, P, V, N, and T. We are told that it is sealed, so we know N1 equals N2. So right away, we can cancel those two. And we know the initial pressure. That's 1.00 atmospheres. We know the initial temperature. Convert that to Kelvin, 298.15 degrees Kelvin. And you'll notice I'm not rounding this until the end of the problem. We're not going to, we convert it as best we can for now, and we'll round to the appropriate number of digits at the very end. You're told it drops to 17 degrees. 17 degrees would be 290. Sorry, 290, pardon my penmanship, degrees of 0.15 degrees Kelvin. And that's horribly written, I realize. Let me rewrite that so it's a little cleaner. We'll put that temperature right in there. I'll just put a little line here. That's 290 even 0.15 degrees Kelvin. And we'll put that in as well. Sorry about my K. we know that this is in a jet airliner. Well, the jet airliner is not going to change volume, so we know the volume is the same thing as the initial volume, so it doesn't change. So the only thing we don't know is our final pressure. So we start with our original equation. We've already canceled out the ends because it's sealed, and it's a steel, aluminum and other metal airliner. This is not going to change volume appreciably, so you can cancel out volumes because they'll be the same. And now we end up with P1 over T1 equals P2 over T2, and this is simply Gay-Lussac's law or Amundsen's law. So always start with the appropriate equation. If you have a one-step problem or one condition problem, you're going to use the ideal gas law for that. And if it's two-step, start with the ideal gas law as a two-step version, as a two-condition version, and then cancel out the things you know you can cancel that are constant to simplify it to an equation that's much easier to use. So let's look at an actual problem. This is a two-condition problem, and it happens to be Boyle's law, but let's make believe you didn't know it was two-condition before you read the problem, and that you didn't know it was Boyle's law. So let's read the question. A sealed isothermal piston, all right, so already you're given a certain amount of information here. Sealed tells you that this has a constant number. Then the initial number will be the same as the final number of moles. Nothing can get in, nothing can get out. Isothermal tells you the temperature does not change, so T1 equals T2. It contains a volume of gas, 2.45 liters, so that's your initial volume. And it tells you that the pressure of that gas is 7.65 atmospheres, so that's our initial pressure. If the pressure is decreased, all right, this is telling you something changes, so now you know it's a two-condition problem or a two-state problem. You can make your table with 3 columns, a column of parameters, and 2 columns for your information. And it says the pressure is decreased to 2.39 atmospheres, so that's your final pressure. What is the new volume? So our new volume is our unknown. And we can write this right on the problem. If you have it on paper, if it's on computer, you're going to have to do this as a separate table. But you now make your table and you fill in your values. You know right away that N1 equals N2. And you know that T1 equals T2. So this simplifies things a great deal. You know your initial volume of 2.45 liters. You know your initial pressure of 6.75 atmospheres. And you know your final pressure of 2.39 atmospheres. Significantly less than your original pressure. About a third of what you used to have. And here's your unknown volume 2. So we're going to solve for that. Now you can jump right to Boyle's equation, that's fine, or we can start with what we know we always start a two-condition problem with. And that is start it with our ideal gas law written as a two-condition problem. We cancel out the n's and the t's on both sides, and we're left with Boyle's law. And I'm going to clear the notes that I've written here. But remember that you have your table, you know your values of your initial and final pressure, and you know your value for your initial volume, and we don't know the value for our final volume. So we rearrange our Boyle's law equation to solve for V2. The easy way to do that is just by dividing both sides by P2, and the P2's cancel, and you're left with this version of Boyle's law. So I'm going to erase some of these special notes here. And now you have your data in your table. I've erased it and put in generic values, P1, P2, V1, V2, but you have your actual values now. And the usefulness of the table is to take those values and then plug them into your equation in the appropriate places in order to solve it. So shown here is the equation with the appropriate numbers filled in, and having a table makes it easy to figure out which one's which, because it's very easy to switch a 1 with a 2 when you're putting the numbers into an equation, especially with some of the other gas law formulas. So we have our equation. You'll notice that atmospheres will cancel atmospheres, and we end up with 7.84205 liters. We round it to 3 significant figures. Why? Well, look at our initial numbers, 3 sig figs, 3 sig figs, 3 sig figs. The lowest of those is 3 sig figs, so we round our answer to 3 significant figures to get 7.84 liters. Now, does this answer make sense? Well, our original volume was about 1/3 of that volume, and our original pressure is about 3 times the final pressure. So that makes total sense. You know that from Boyle's law, one will go up, the other will go down, and they go up and down by the same ratio, the same factor. So if the pressure is increasing, if the pressure is decreasing by 3-fold, the volume will increase by 3-fold. And that's exactly what we see here. So let's look at the next problem. How many moles of air are in a sealed 2.0 liter bottle at 19 degrees centigrade or Celsius and 747 millimeters of mercury pressure? So we see that this is a one condition problem. Nothing is changing. We're just being asked for a missing parameter, moles, and we know a volume, we know a temperature, and we know a pressure. So this tells us we're going to use the ideal gas law in the one state form, or the one condition form. And that's PV equals nRT. We're going to solve for N because we're being asked for the number of moles. And at this point, we have our formula, but it's always good to make our table. So we're going to start our table as usual. And we have only a one condition set, so we'll just write a 1 at the top here. We've got our P, we've got our V, we've got our N, and a T, and if you'd like, you can always remind yourself which R you're going to use, and that will be based on the units that are involved in the problem. We have a sealed 2.0 liter bottle, okay, so we know the volume is 2.0 liters. At 19 degrees C, well, we can write the 19 degrees C, but we're going to need to convert it to Kelvin. We're going to add 273.15 to that value. We'll end up with 292.15, and that's shown in the problem itself, so you don't have to worry about if you don't see it right here. We don't know the number of moles, that's our unknown, and our pressure is in millimeters of mercury, or torr. Those are the same unit, millimeter mercury. So that tells us that our R value must be the one that's in liters, millimeters of mercury per degree Kelvin mole. And we know that value, we can look that up. And then we're going to plug our various values into our final formula, and that's shown here. And the R value in this case is this value shown here. You see the T is calculated, 292.15 Kelvin, because that's what you have to use. Always use Kelvin in these problems. And we have our pressure and our volume at the top. We've got our pressure here, and we've got our volume here. And now it's just a matter of plugging these numbers into your calculator and solving for the answer. I'm going to erase some of these notes here, and we'll continue on. And we get a value of 0.081999 moles. And you'll notice that if we look at our equation, this number has 3 sig figs. This one has only 2 sig figs. This one that we're using temporarily looks like it has 5, but it's really just 2. We haven't rounded it yet. And this one has 5 sig figs. So the lowest number of this is the 2 sig figs. So we're going to have to round our answer to 2 significant figures, or 0.082 moles. Let's look at another question here. What is the pressure in atmospheres exerted by 1.8 grams of hydrogen gas in a 4.3 liter balloon at 27 degrees C. Okay, so first thing you need to notice is this is a one condition problem, a one state problem. Nothing's changing. So you're going to be using the ideal gas law to figure out the missing parameter. In this case, the missing parameter is pressure. But you'll notice we're given a volume. That's good. And we're given a temperature in degrees centigrade, which we have to convert to Kelvin, but we have a temperature at least. And you'll notice this is not a number of moles or particles of hydrogen gas. It's a number of grams, so we're going to need to convert that. So the first thing we're going to need to do after we realize what formula to use, which is the PV equals nRT, the one state, one condition ideal gas law, we solve for P. But the first thing we need to do after that is to calculate how many moles of hydrogen we actually have. And before you can calculate moles of anything from grams, we need the grams per mole. That is the molar mass. So the molar mass of hydrogen gas, H2, is just 2 times the molar mass of a single hydrogen atom. And then you multiply that out and we get this value. Remember, this value, every molar mass is a conversion factor. It tells us that we have 2.01588 grams of hydrogen is the same thing as 1 mole of hydrogen. So I'm going to erase some of these notes that are causing a little clutter here. We're going to take this out for now. And now we know our molar mass, so we can convert our 1.8 grams of hydrogen gas to moles. And we use the molar mass as a conversion factor, putting the grams on the bottom and the moles on the top, because the grams of hydrogen will cancel grams of hydrogen, and we'll be left with moles of hydrogen. And you'll notice I'm not rounding this number yet. We don't want to round early. We avoid what are called rounding errors. So we're going to use this as our moles. Now we have our N, we have our V, we have our T that was converted to 298.15, I'm sorry, let me change that, 300.15 degrees centigrade, Kelvin, 300.15 degrees Kelvin, and we have our moles, our N. So now we have our 3 parameters. We just need the appropriate R value, and we are using atmospheres, so our R value will be the liters atmospheres per degree mole, and that will be the R value of 0.082057, and we plug those in, and those numbers are all shown here. So we have our N, we have our R, we have our corrected T, and we have our V, and we can put this in our calculator, and we end up calculating a pressure of 5.114 atmospheres. You'll notice while this number has 4 significant digits, it was from a number with only 2 significant digits. So it's really 2 sig figs for that number. And this number started with 2 sig figs as well. And this number, the volume, started with 2 sig figs. So we need to round our answer to 2 sig figs, or 5.1 atmospheres. Here's another problem. 15 liters of gas in a sealed piston, we know what sealed means, at 4.8 atmospheres pressure at 25 degrees centigrade is heated to 75 degrees C and compressed to 17 atmospheres. What is the new volume? Well, first of all, we know it's a 2-condition problem because something's changing. In fact, a few things are changing, 2 of which we're told about. And we're asked for the new volume. That's the third thing. So we know things are changing. We know we have a 2-condition problem here. And we need to make our table to keep track of all of our different values. So we've got our pressure, our volume, our number, our temperature. We know that we're starting with 15 liters of gas, so we can write that right here in our V1. We don't know our new volume, so that's our question mark. V2 is our question mark. We have an initial pressure of 4.8 atmospheres. Our final pressure is 17 atmospheres. So we're increasing our pressure considerably, and our temperature was 25 degrees C, and it will become 75 degrees C. So we know we have to convert both of these to Kelvin before we do anything. And we're going to add 273.15 to do that. So this will be 298.15 degrees Kelvin. And this one will be 348.15, a little hard to read, degrees Kelvin. So we have our two temperatures, and we see that it is sealed. So that tells us that N1 equals N2. So the only thing we're missing is V2 here. So we're going to start with a two-step ideal gas law equation. P1 V1 over N1 T1 equals P2 V2 over N2 T2. We know the N's are the same, so we can just cancel them out, and we end up with the combined gas law. And you don't need to memorize the combined gas law. It's just a subset of the ideal gas law in a two-condition form. So we have this, and I highly recommend when you're working with formulas that have a fraction equals another fraction, just cross-multiply them to get rid of the fraction. It'll make your life a lot easier for the math. So we would multiply the top of this with the bottom of this, and we would get temporarily 1 P1 V1 times T2, and then we multiply these together, and we end up with P2 V2 over T2, and now this makes it much easier to solve for V2. We just divide both sides by P2 and T2. And doing so allows us to cancel that, and this is simply V2, which I have written right here underneath this mess. So I'm going to erase a considerable part of this so you can see it all worked out. And I'll keep this a little clean here. And we have our table. And now we have our values. We have our final formula shown here. And we have our table that will keep us from making mistakes by putting in the wrong value into the wrong variable. So now we're going to continue on. We plug these numbers in, and I've shown you the adding of the 273.15. I would recommend you do that in advance, but I'm showing it within the formula so you can see it done for you. And now you have your values plugged in. Make sure everything is in the right place. Multiply it out, and you see our answer is 4.9456 liters. Looking back at the original problem, 2 significant digits, 2 significant digits, 2, 2, 2. So our final answer has to be in 2. So our final answer is 4.9 liters of volume, which is the new volume. And since both pressure and temperature changing, it's really hard to do this in your head and ask yourself, does this make sense? You just have to be really careful with your calculations. And here's the last problem of this set. If 6.2 liters of gas at 723 millimeters of mercury, that's pressure, and 21 degrees centigrade is compressed to, okay, we know it's a two-step because something's changing, compressed to 2.2 liters at 4,117 millimeters of mercury. So we're changing both the volume and the pressure. And the question is, what is the final temperature of the gas? So we're going to set up our equation just like we did before. And we still end up with a combined gas law because this is a container. It mentions nothing about the number. It should mention that it's sealed. But since it doesn't, you're going to assume that it's sealed and that the N1 is equal to N2 and that you can cancel it. Remember, cross-multiplying this will make it much easier to solve for T2. I'm not going to go through that again. Make your table make things simple for yourself. So you get your table of first condition, second condition, P, V, N, T. We're going to assume that N1 equals N2. And we are given an initial volume, 6.2 liters. We're given an initial pressure, 723 millimeters of mercury. I'm going to write torr because it's a little easier to fit in here. And the final pressure is much higher, also torr or millimeters of mercury. And the final volume is 2.2 liters. And we know that the initial temperature is 21 degrees centigrade. Well, 21 degrees centigrade, you have to convert to Kelvin. We're going to add that to 273, so that's 294. And I'll put in the 0.15 degrees Kelvin. And then our final temperature, we don't know. But when we calculate our final temperature, it's going to be in Kelvin. And we are going to need to convert it back to centigrade because the problem is in centigrade, so you're required to change it back to centigrade. So now you have all your values to plug into your T2 equals formula. So let's plug that in. We have our final pressure on the top, our initial pressure on the bottom, our final volume on the top, our initial volume on the bottom, so make sure you don't mix those up, and you have your initial temperature on the top. And now you plug this into a calculator, and you end up with 564.35 degrees Kelvin. And there are a couple issues with this. Number one, it's too many sig figs, and number two, we want it in centigrade or Celsius. So first, let's just subtract off the 273.15 to get it in centigrade or Celsius. And now, since our smallest significant digits in this problem are 2 sig figs, we want to round our temperature to 2 sig figs or 320 degrees centigrade. And that's it.